Okay, so we just started 8.1 last class. Where's everybody? And we need to finish up 8.1, hopefully get into 8.2 today. Last time, really what we spent a lot of class doing was I would give you a sequence, and then we try to come up with a formula for it, and just gave you a few problems out of the homework. One thing that did come up, questions about the homework, is does your answer always match the back of the book? And the answer is no. Sometimes your representation of the sequence may look different than the back of the book, and it still may generate the correct sequence. So don't be looking for your answer to necessarily match. It just needs to create the same sequence. So the answer is not unique. All right, we're going to start today with the limit of a sequence. So let's say we're given some sequence, a sub n. Now there's different notations. I could have written a sub n, or I could have written a set of braces, a sub n, or I could have written something like a sub n equals 1 to infinity. All of those would be the same thing, but we're going to represent a sub n as just a sub n, like this. And this really means this. And let's say that it is an infinite sequence, all right? So let's say we're given an infinite sequence. If we write limit n goes to infinity of a sub n equals L, or we write this, a sub n with an arrow to L, then we mean by this, as n gets large, a sub n gets closer and closer to the value L. Would you mind shutting the door, please? Franny, thank you. So we did this in Cal 1. We investigated limits, and we let like x go to something, and then the function went to a value. This is the same concept. The only difference is that we are going to let n go to infinity here. So what we're wanting to do is figure out what is this sequence behaving like as we go out further and further into the sequence. Are these numbers getting closer to a specific number, or are they getting infinitely large? I mean, what's happening? So let's start with an example. We'll take a very simple one. Let me define a sub n to be equal to n. Now, if we look at this sequence of numbers and write them out, what would this list of numbers start with? 1, then 2, then 3, and then it keeps going like this, right? This infinite sequence. So what is a sub n approaching? Okay? It's becoming infinite, right? What you're essentially doing is this. You're saying let the limit, take the limit as n goes to infinity of n, right? Because n is our sequence. Our sequence is n. N is here. Let n go to infinity. The thing becomes infinite, right? This is headed towards or equals infinity. So each term of the sequence getting larger and larger and larger. Make sense? Pretty simple? Let's do another one. What about the sequence a sub n equals 1 over n? So what's happening here? We start off with 1, then 1/2, then 1/3, 1/4. What in the hell is going on with this thing today? 1/4, and it keeps going, right? So a sub n is approaching what here? Limit n goes to infinity of 1 over n. And back from Cal 1, if your numerator is fixed and your denominator gets large, that ratio gets small. So I hope it's obvious that that would go to 0. Yes? All right. So we have the first example, the sequence got huge, right? Went to infinity. The second one, it went to 0. 0 being a fixed number, infinity not being a number, right? So we have different terminology here. If it goes to a fixed number, we say the sequence converges. If it does not go to a fixed number, we say it diverges. So definitions here. Convergence and divergence. So if a sub n goes to L with L finite, what do I mean by finite? It's a number, right? If it goes to L, and L is a finite number, then we say a sub n converges. Otherwise, we say a sub n diverges. Now there's something subtle here that I don't want you to miss. And that's if the sequence goes to a finite number, convergence. Any other cases, we say it diverges. What I'm not saying here is that if it goes to infinity, that's the only way we can say diverges. All right? Let me give you an example of something that diverges that does not go to infinity. All right? Here it comes. Here's an example. A sub n equals cosine n. So let n go to infinity here. What does cosine do as you go to infinity? It's, yeah, as far as a graph of it, it would oscillate, right? But remember, we're not looking at a solid, nice, continuous graph, right? Remember, sequences were just dots. So I have a visual here. It's a little code I wrote up. Let's look at that first sequence we did. It was n, right? Where are they? There they are. Okay. That's the sequence n, all right? You plug in 1, you get 1, then 2, then 3, then 4, and right? And look at this thing. It just goes out. A sub n goes to infinity. You see it? All right, let's do 1 over n. So we plugged in 1, we got 1. We plugged in 2, we got a half, and then a third, and then a fourth. So you can see this one converges, right? These get closer and closer to 0. They're kind of following this red line a little bit, right? But the black dots represent a sequence. The red line's just there as an aid. Now let's try cosine. Okay, so here's the cosine, right? Here's the cosine. It's going back and forth. But we're looking at these dots. And let me go out further. If you focus just on the black dots, is it converging to anything? No. It's not going to a fixed number. They're scattered everywhere, aren't they? And it's not going to infinity, right? but it's not going to a fixed number. Since it's not going to a fixed number, this diverges. Understand? A lot of times students will think, okay, well, if it has to go to infinity to diverge. No, not the case. So this one right here, limit n goes to infinity of cosine n. That limit does not exist. All right, we would say that this limit does not exist. Therefore, 3 dots means therefore. We've seen that before. Have I shown that in class? Yes. Okay. Therefore, a sub n diverges. We good? Understand? Another example of one that would, well, you tell me. This is an interesting one. A sub n equals -1 to the n. So that's that sequence that we used when we wanted to create alternating, right? It was -1, 1, -1, 1, and it kept on doing this, right? Does that converge or diverge? It diverges, right? Because it's just jumping back and forth between -1 and 1. You can't say it's going to 1 because then it goes to -1. You can't say it's going to -1 because it goes up to 1. So this one also would diverge. Okay, now when it comes to limits of sequences, we have a bunch of properties, and I don't want to write them all down. So they're on page 429 of the book. I'm just going to read through these, all right? It says, if A sub n and B sub n are convergent sequences and C is a constant. So, very important to understand that these limit laws, these limit properties, only hold for convergent sequences. You cannot use these properties if your sequence is divergent, all right? So assuming that the two sequences we start with are convergent, then if you want to take the limit or want to see what happens when you add the two, you can do each one separately. So you can split them up into two separate limits. If you do subtraction, same thing. If you multiply your sequence by a constant, you can pull the constant out and take the limit of the sequence. The limit of a constant is a constant. If you multiply two sequences together, and you want to know what's happening is let n get bigger, just do each one separately, multiply the two answers together. Again, you have to have convergent sequences for this to work. You take the ratio of two convergent sequences, or the limit of two sequences, you can do the limit individually, so long as this limit on the bottom doesn't go to 0, and that's just because you can't have division by 0. And then the last one, this is a very important one. It says if you have the limit as n goes to infinity of a sequence raised to a power, you do not have to figure out what the sequence to the power is first. What you can do is figure out what the limit of the sequence is, then raise it to that power, so long as the power is positive and the sequence is positive. So that really tells you that you can pass the limit through the power. You can move it into the power. All right, so we've got those properties. And then we have, after that, what's called the squeeze theorem. I'll just put here, page 429, just to reference C properties. Now, squeeze theorem. All right, so I'm going to bring up the book again to show you what the squeeze theorem says. Here it is. It says, if you have three sequences, A sub n, B sub n, and C sub n, three different sequences, and they maintain this inequality, meaning the A sub n is smaller than or equal to the B sub n, which is smaller than or equal to the C sub n, and that inequality holds as long as n is bigger than n naught. What does that mean? N naught doesn't necessarily have to be 1, okay? N naught is just, remember, n starts at 1, then 2, then 3, then 4. This is saying that this inequality holds eventually for some n bigger than some, let's say, initial n, which could be 1, could be 10, could be a billion. So these sequences may be jumping around on top of each other back and forth, but eventually the A is below the B is below the C. Got it? If that's true, and the limit as n goes to infinity of A sub n, so that's the one on the bottom, is equal to the limit as n goes to infinity of C sub n, which is the one on top, then what must the one in the middle do? The same thing. Then the sequence in the middle must be squeezed between those two and approach the same value. So let me show you just a graphical representation. Let's see, if we have, let's say we have a sequence in red here. Let's say it does this, 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 this. Okay, let's say it does that, right? Let's say that's A sub n. Then let me give you a B sub n, or C sub n. Here, 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 here. That's B sub n. Sorry, C sub n. So what I have, and I should probably have to continue these out so you can see the pattern a little more. Let's say A sub n does that, B sub n. It's getting closer. Do y'all see that? So A sub n is below C sub n all the time? No, eventually, right? Right, I'd say right around here, right around in this spot. This would be like our n naught, right? Before n naught, they don't maintain that inequality, but after a certain point, the blue one's on top of the red one. And look, they're both going towards the same value, aren't they? So they're both going towards, let's say, some asymptote here. It's like a line. This line, if I extend it this way, the value of that is L, okay? So if we have some third sequence, B sub n, which I will do in green, and it's doing something, but then after n naught stays between those two all the time, then the B sub n has to go to the same limit. Do you understand geometrically what's happening? Okay. So how can we use this to figure out some interesting, let me do one of these. Where's the one I wanted? Man. Okay, here we go. Let's do this example. Does this converge or diverge? So here it is. A sub n equals sine 2n over 1 plus the square root of n. All right. So does it converge or diverge? So what we need to do is figure out what the limit as n goes to infinity is, right? So what is the limit as n goes to infinity of sine 2n over 1 plus root n? So what do you think? What's happening on top? As n goes to infinity, what does sine of 2n do? It's going to diverge, right? It's going to be popping around up and down, but just dots. And the bottom goes to what? 1 plus infinity. So you don't have fixed over infinity like you did in Cal 1. If you have fixed over infinity, then it goes to 0. I'm sorry? Sine's diverging. That doesn't mean it's going to infinity, though, right? So you don't have infinity over infinity. Let's just say, though, for the sake of argument, and because I want to make a point here, let's say you did have infinity over infinity. You would be thinking L'Hopital, right? Here's the problem. L'Hopital's rule works when you have two functions, right? Yes? And the way it works is if you have, L'Hopital says what? If you have a function divided by a function, you take a limit, this is going to 0 over 0 or infinity over infinity, that you can take derivative top and bottom separately, right? And then figure out that limit. Well, when I say take the derivative, I'm saying find the slope of the tangent line, right? Yes? You have dots here. You don't have curve. How are you going to find the slope of a tangent line? Like if I just pick one of these points here, right? If I pick a point right here, imagine the red's not there. What's the slope of the tangent line? It makes no sense. To be able to take a derivative, you need to be able to approach. Remember I don't know if you remember this. The definition of the derivative was the limit as h goes to 0 of f of a plus h minus f of a all over h. That's the definition of the derivative, which meant that you had to be able to approach from both sides. You can't approach a point from both sides. There's nothing there to the side of the point. So L'Hopital's rule is out. Okay? It is out. We cannot use it. Well, we're going to have a workaround, but for now we can't. So we are kind of stuck here. We didn't even have infinity over infinity, right? We didn't even have it. We have undefined or divergent sequence over an infinite sequence. Now, our logic is probably telling us this should go to 0, right? Because the top is bounded between two numbers, -1 and 1, and the bottom just keeps getting bigger. But we're going to have to use the squeeze theorem to prove this. All right? So how can I use the squeeze theorem here? Let's see. Yeah, that's right. That's right. So let me try and do this. If I'm going to use squeeze theorem, what I need to do is I need to somehow get sine of 2n over 1 plus root n. I need to get it squeezed between two things for all n greater than or equal to n naught. I need to figure out what I can squeeze this between. This between 0 and pi, is that what you said? How are you coming up with 0 and pi? I know this right here, 0, can't this be negative? Sine can turn out to be a negative number, couldn't it? Sine of 2n? So I can't use 0, but hold on. I'm trying to squeeze it between two things, right? And what I need to make sure is that these two things, when I take the limit and I let n go to infinity, I need this one to go to L, and I need this one to also go to L. They have to go to the same thing, don't they? And then I can squeeze that one in the middle. You need to generate these on your own. What's a lower bound and an upper bound for this? Okay, so watch me do it, all right? I'm going to start with using sine of 2n. I know that for sure is between -1 and 1. Do you agree with that? Yes? Okay, so I'm starting my work here. That is a guarantee because of the definition of sine. It's always between -1 and 1. Now, what is it that I needed to have in the middle? This over 1 plus root n. So how about I divide this by 1 plus root n? If I do that here, I have to do it to every one of these, right? So I'm going to come in here and I'm going to divide by 1 plus root n. Now, there is a danger here. There's a danger zone because we're working with inequalities, right? Not equalities. Don't you have to flip inequalities over sometimes? If you divide by negative. What about 1 plus root n? Is it ever negative? No, that's never negative, is it? So I don't have to take that into consideration. So I'm okay to do this and not worry about flipping signs. Now, is that enough? What happens to this as n goes to infinity? Let n go to infinity here. It goes to what? Fixed over infinity goes to 0. This over here, same thing, right? 0, which forces this to go to 0. It has to be between 0 and 0, right? The only number between 0 and 0 is itself. That's how the squeeze theorem works. You have to come up with some sort of control that you know for sure will happen. This one was pretty obvious. Sine is between two things, and then you just kind of massage it to make it look exactly the way you want it. All right? Questions on squeeze theorem? Okay, let's try some more stuff that's not so obvious. How about this one? I want you. This is not necessarily squeeze theorem. Okay, just tell me if this converges or diverges. Let's do a couple of parts. Part A sub n equals 0.999 to the n. What is that? As n gets bigger, this thing gets smaller, right? Because 0.999 is less than 1. If it's less than 1, it gets smaller as you raise it to bigger powers. Are you all comfortable with that? If it's bigger than 1, it goes to infinity, right? So this would converge to 0. Part B. What if a sub n equals 2 to the n plus 2 over 3 to the n? What does this do? Converge or diverge? The top's getting bigger, right? 2 to the n's getting infinite. The bottom is also becoming infinite. So you have two divergent sequences, don't you? So you're thinking what? Divergent or convergent? This is the same thing. 2 to the n plus 2 is the same as 2 to the n times 2 to the 2, because you add the exponents, right? And then 2 to the n over 3 to the n is the same as 2/3 to the n. And then what was still sitting out here? 2 to the 2, so 4 times 4. What does 2/3 to the n do? It goes to 0, doesn't it? This goes to 0. We just said that a number smaller than 1, if you raise it to bigger and bigger powers, gets smaller. So this is going to go to 0. 0 times 4? It's going to go to 0. So our conclusion here is that this a sub n also goes to 0. That's all based on the fact that this number right here is less than 1, right? Make sense? Okay. How about a sub n equals the square root of 5n plus 1 over n plus 3. Yay or nay? You got that or not? Diverge. What does this go to? Infinity here? Infinity, infinity over infinity? Don't really know. Got to figure it out. Now, how would we handle this if this was 5x plus 1, x plus 3 under square root? You could have used L'Hopital, right? You could have. And if you do L'Hopital, you could actually go inside the root and then go ahead and figure out what infinity over infinity here is, and it would be what? Take derivative of top and bottom, and you get what? 5 over 1, which would be 5. So the answer here should be square root of 5, if it was a continuous function, right? But it's not. So what we have to establish for this is a theorem, all right? And the theorem is on page 430. Here it is. Continuity and convergence theorem. If the limit is limit as n goes to infinity of a sub n equals L, right? So let's say we have a convergent sequence, right? That's what this means. If it's true that it's convergent and f is continuous at L, then the limit as n goes to infinity of the function evaluated at the sequence is equal to the function's value at L. What the hell is that? Oops. Yeah, I want that moved down. Let me write this in a different way. We're going to put this on hold just for a second. If a sub n is given and we define f of n as a continuous function on R, then if the limit as n goes to infinity of f of n equals L, then a sub n converges to L. All right, so I'm going to try and show this to you with an example, like a visual. Back here, change this to 1 over n again. We know that 1 over n converged to 0, right? What I just wrote down here is saying that if we're given a sequence, and instead of just looking at the dots, we look at the function, that sequence as a function, but we now extend its domain instead of from the positive integers to the real numbers, and that function has a limit, then that sequence must go to the same place. So in the picture, the red is us extending the sequence to the function, the continuous function. This is like 1 over x, isn't it? Whatever the 1 over x does is what the 1 over n as a sequence has to do. So this is just a domain change. So anything that applies to the red must apply to the black. Make sense? So when we go back to this problem where we had stopped, we said, man, we'd really like to change this and make it so we can use L'Hopital's rule. That theorem tells us we can, right? So we're allowed to, but you have to state it. You have to let whoever's reading your work know you're not trying to use L'Hopital's rule on a sequence. You're using it on a continuous function, then using that result to determine the result of the sequence. It's not just L'Hopital's rule automatically. So I'm going to continue that one now. So continuing here. we were trying to find for a sub n equals square root 5n, what was it? Plus 1 over n plus 3. Okay, I'm gonna write down here, let f of n equal this. For n in the real numbers and n greater than or equal to 1. So I'm letting you know right now, I'm going to define a function. The function is going to be exactly the same as the sequence, where the number I'm plugging in, n, is going to be a real number instead of an integer, but I'm going to start at 1, just because my sequence starts at 1. I don't need to look anywhere else. Now, the limit as n goes to infinity of this function is going towards the square root of infinity over infinity, right? I need a new page. Are y'all with me? What's most important here is me writing this stuff down and you getting used to needing to write this down, right? Explaining what you're doing. So this gives us square root of infinity over infinity. So I have the limit as n goes to infinity of the square root of 5n plus 1 over n plus, man, what is going on with, my computer is acting really weird, plus 3 equals the square root of the limit as n goes to infinity of 5n plus 1 over n plus 3. So what did I do there? Just pass the limit through the root, right? I can do that from Cal 1. We were told we can do that in the Cal 1 class. And now this right here, I'm going to apply L'Hopital's rule. So by L'Hopital's rule, you can use an L or an H, doesn't matter. The square root of the limit as n goes to infinity of 5 over 1, which equals square root of 5. Right? Derivative of top and bottom. Therefore, a sub n goes to root 5. Okay? A sub n goes to root 5. I have to state that at the end. And this may seem like you had the answer here. Why do you have to write that down? Because this is not the answer to what the limit of a sub n is. This is the answer to what the function is going towards, right? F of n. And we have that theorem that says whatever f of n goes to is what a sub n goes to. So we draw our final conclusion right here. Shall I give you an example? Yes. Okay. Limit, a sub n equals, stick with the something within line of the book. Okay. 5n factorial. 5n factorial over 5n plus 2 factorial. Okay, so somebody tell me why this is going to be an issue. Why you can't use what we just did. Yes, we can. We can break down the factorial, but what I'm saying is why can't we use that theorem? Because the question was, well, why can't we just always use the theorem? I just look at it as a function and use L'Hopital. You cannot define that as a function on the real numbers. Okay? This The last function, sure, you could look at the graph of that. If I ask the computer to graph this, there's no way to do it and be able to plug in like 1/2. You can only plug in like 1, 2, well 0, 1, 2, 3, 4. So I don't have an analogy of a true continuous function, do I? So I can't take derivatives if I don't even have a function. Does that kind of make sense? So how would we deal with this? Well, we want the limit as n goes to infinity of 5n factorial over 5n plus 2 factorial. And we know that the top goes to infinity and the bottom goes to infinity. Agreed? Like, let n get bigger. 5 times in big numbers, big number. Factorial is huge number still. So that's infinity over infinity. Cannot use L'Hopital's rule because you can't turn it into a function on the real numbers. But we learned about factorials last time, that you can start peeling factorials off. Remember that? So I'm going to leave 5n factorial on top alone. I'm going to rewrite the bottom as what? 5n plus 2, 5n plus 1, 5n factorial. So the 5n factorial, this piece right here, is what would be the rest, right? Dot, dot, dot. But that's exactly what 5n factorial is up here. So these cancel. And all you're left with is limit n goes to infinity of 1 over 5n plus 2 over 5n plus 1. And what happens here is n goes to infinity. It goes to 0. So your answer is 0. Mm-hmm. We are mostly interested in convergence stuff. I'll let you mess with the rest on your own. A couple of other theorems. I don't want to do too many examples. Theorem. If the absolute value of a sub n goes to 0, then a sub n goes to 0. Example. Converge or diverge here? Does this converge or diverge? The top is going what? -1, then 1, then -1, then 1. It's going to oscillate positive and negative, right? But they get smaller. Okay, let's just look at this theorem, though. What does the theorem say? Let's take the absolute value of a sub n. What's the absolute value of a sub n here? Absolute value of -1 to the n over n. When you take the absolute value of -1 or 1, right, on top doesn't matter. What is it? 1. And then over the absolute value of n, which is just n, because n is positive, right, so it doesn't matter. So the absolute value of a sub n is 1 over n, and what does 1 over n go to? We already know that. That goes to 0. So if the absolute value of a sub n goes to 0, then so does a sub n itself. So that means the conclusion is that, what? -1 to the n over n also goes to 0 by theorem. Above. Yes. Good question. That's right. That's my next example. You have a question, though? Okay, negative 1 to the n is either 1 or negative 1, right? There's only two possibilities. And when you take the absolute value of that, it's always 1. Got it? The book doesn't, I don't think it references a name. Nope, there's no name. No. Theorem 4 is what the book, no, Theorem 6. Okay, yeah, so let's look at a different example. What if you have a sub n equals negative 1 to the n? Well, that's going to give you negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. So maybe you start to come in here and say, all right, well, I'll take the absolute value of it, right? What's the absolute value of negative 1 to the n? That's always just 1, right? So does this mean, since the absolute value converged to 1, does that mean this one converges to 1? No. What does the theorem say? If the absolute value of a sequence goes to 0, and it must be 0, then the sequence itself goes to 0. If the absolute value goes to something other than 0, the theorem fails. I mean, it's inconclusive. So that means we don't have a conclusion. We can't use this theorem. So theorem does not apply. It would be divergent. The reason why it's divergent is because this sequence oscillates back and forth between 1 and negative 1. We knew that. We already had done this example, right? But I'm just showing you how you could have to be careful and not use that theorem incorrectly. Okay, more stuff. Let's do another one. Another example. What's the limit as n goes to infinity of 1 plus 1 over n to the n doing? I'm going to shut my web off here. Unplug my network. You recognize that? Yeah, you should. 1 over n is going to go to what? 0? 1 plus 0 is getting close to 1. So what's happening is that right now the base is getting close to 1, right? Everyone understand? Close to 1, not 1. It's getting close to it. And the exponent is getting very, very big. And this in a Cal 1 class is called an indeterminate form. Your base wants to become 1, and 1 to any power should be 1. But it's a little bigger than 1, and anything bigger than 1 when you raise it to a huge power wants to get big. So there's this battle happening. There's not a whole lot more we can do, but in Cal 1 we had a way of dealing with this, and it involved L'Hopital's rule and things like that. So the first thing we need to do is take this sequence and convert it over to a function over the real numbers. So I'm going to start this out by letting f of n equal this. Where n is a real number and n is greater than or equal to 1. I'm using greater than or equal to 1 because that's all I care about, right? Is this a nice continuous function? Except at 0. That's the only place we have a problem, right? So I can graph this and I can figure out where it's headed. But the way we're going to do this, the way we're actually going to figure out this limit is we're going to try and take this limit, right? We're going to let n go to infinity on this. See if you remember this from Cal 1. We define this limit to be something, anything we want. I'm going to call it y. And then we take the log on both sides. Take the natural log on both sides of this equation. When you do this, you can pass the log through the limit on the right side. And why is it that we come in with the log? Anyone remember why I brought log in on both sides? Because that'll allow me to do what? Bring the n down in front of the log. You can't bring it out the limit because n is controlled, so, or n is changing, so it has to stay in there. Okay? So I drop that n down. That's a property of logs. And now just take a quick check of what's happening here. N goes to infinity. This right here goes to infinity. So what I'm getting is something that looks like infinity times, let's see, 1 over n we said was going to 0. 1 plus 0 is going to 1. Natural log of 1 is 0. So we have something that's getting very, very big times something that's getting very, very small. That's still an indeterminate form in Cal 1. So now what I need to do is convert it over to, instead of infinity times 0, to either infinity over infinity or 0 over 0. And so what we do, see if this rings a bell. I'm going to pick one of them. In this case, I'm going to pick the n. And I'm going to rewrite it in the denominator, like this. It doesn't matter, but a lot of times what you're going to do next will dictate which one you should use. N is going to be rewritten as 1 over n in the denominator. That's the same thing. And by doing it this way, if I let n go to infinity, we already know that the top wants to become 0. But instead of having infinity out here, 1 over n on the bottom becomes 0. So now I have 0 over 0. And then I can use L'Hopital's rule. That's right. Because I am working with a continuous function on the real number system, I can do L'Hopital. So the natural log of y, oh, I should write over here. This is now 0 over 0. So L'Hopital. So here we go. Natural log y equals, by L'Hopital's rule, I'm going to take a derivative of top and bottom. What is the derivative of natural log of anything? 1 over that. Anything, right? Times the chain rule. What's the derivative of what's inside the natural log? So derivative of 1 is 0, plus what's derivative of 1 over n? Not antiderivative, derivative. Negative 1 over n squared. Or you could have said negative n to the negative 2. But that's a derivative of 1 over n. And then on the bottom, hey, check it out. What's the derivative of 1 over n? We just did that. It's negative 1 over n squared again, isn't it? And what happens? These cancel, don't they? Now let n go to infinity. 1 over infinity is going to be 0. 1 plus 0 is 1. 1 over 1 is 1. So the right side becomes 1. I'll put that over here. I don't want to do a new page. I have natural log y, that's the left side of the equation, equals 1. And remember what it is that we were looking for. Way up at the beginning of the problem, I said, look, this limit that I'm trying to find, I'm going to call it y. I did that out of nowhere because I knew I needed natural log on both sides. So over here, I need to get back to y. So how do I get y out of a natural log? I do e on both sides. When you take e of natural log, they kill each other off. They're inverse functions. So that spits out y. So the answer is e. So this limit is e. Therefore, a sub n approaches e. It is a convergent sequence. Questions? E is like pi. That's right. That's right. That's right. Yes. Yep. In fact, you could define E to be this. You could define that to be E. Yeah, but it's even easier with pi. The most common irrational numbers that people know are these. Those are the most common irrational numbers that people in math know. Irrational, non-repeating, non-terminating decimals, right? Pi is very easy to define. Pi is just if you take a circle, diameter, circumference, pi by definition is circumference over diameter. It's a very, very simple definition for pi. The square root of 2 is actually easy to define geometrically also. It's the hypotenuse of a right triangle with two legs, 1 and 1, right? Pretty easy to define what the square root of 2 is. E is not so easy. You could define E to be the limit as n goes to infinity of 1 plus 1 over n to the n. That's an appropriate definition for E. So is 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 plus ... It's an infinite series of numbers, which we haven't studied this yet, but that's where we're kind of headed. There's 1 over n factorial. 1 over n factorial. Okay. That's to answer your question. Hopefully that did. Let's keep moving. Let's look at this just to make sure we're all clear on this. Let's say we have a sequence r to the n, where r is a real number. Then the sequence is r squared, r cubed, r to the 4th, right? And it keeps going forever. Tell me when this thing is going to converge. In other words, tell me what the limit as n goes to infinity of r sub n is going to be. So what if r is bigger than 1? If r is bigger than 1, it's going to become infinite, isn't it? What if r is less than 1 but bigger than 0? Should approach 0, right? So what I'm going to do is I'm going to give you what we would consider to be a piecewise definition here. It'll go to infinity, or we should say it diverges, if r is greater than, I won't put equal, greater than 1. What, now, that was if r is bigger than 1. I think everyone here was agreeing that it would diverge, right? And you said if r was less than 1 and greater than 0. So can I say less than or equal to 0 then? Then this would be 0. What if r is 0? What's 0, 0, 0? I mean, it's just going to stay 0, isn't it? What if r is 1? The answer is just 1, right? Okay, now we have not looked at something here. What if r is negative? Mm-hmm. It would alternate, yes. Okay, so let's start with some numbers that are big. Like, let's say -2. What would happen if you put -2 in here? -2, then 4, then -8, then 16, then is that going to a specific number? Is it going to infinity? Well, positive big number, then negative big number, then positive big number, then negative big number, right? So it's not going to infinity, but it's not going to a fixed number, so we could say it diverges, couldn't we? All right, so what if the number here is negative, but it's a small number, like -1/2? Then it'd be like -1/2, then +1/4, and then -1/8, and then +1/16, and then those are getting smaller, right? Approaching 0. Who cares about the positive negative, right? It's actually going to 0. So what we need to do is we need to tweak this. We need to tweak it to apply to all the real numbers. So how can I tweak it? Absolute value. Okay, good. If I put the absolute value of r is bigger than 1, then I can't say infinity though, remember? But what I can say is what? Diverge. Scrap infinity. Do you agree if the absolute value of r is bigger than 1, it's going to diverge? If the absolute value of r is less than 1, then this thing should go to 0, shouldn't it? That means if you're on the number line, 0, here's 1, and here's -1, as long as you pick a number somewhere in here, start raising it to powers, that's going to get smaller and smaller. What if r is equal to 1? It's just 1, 1, 1. What if r is equal to -1? What if r is equal to -1? It's going to alternate 1, -1, which diverges, right? Okay, so let me see if I can get this on the number line. The green is convergence, okay? Green is convergence. We know that the stuff bigger here, the blue is divergence, yes? What about at 1? It heads to what? If r is 1, it's 1, right? That's convergent. So that point would be convergent, but at -1, it's divergent. Do y'all see that? So I could add one more thing here. I could put r, if r is -1, then what? Diverge? Okay, do you see that? Yes? Now that's not the way the book is going to approach it, all right? I mean, they're going to just simplify this as clean as possible. So look at this last adaptation of this result that we got. Let's see what the book says. The book says that this will be the following. Converges if the absolute value of r sorry, hold on. Converges if -1 less than r less than or equal to 1. Diverges So what this concludes is, this is saying, look, if you're bigger than -1 all the way up to 1, including 1, we're not talking about what it converges to. We're just going to tell you it does converge, right? In this table, we actually knew it was 0 or 1, didn't we? But this is just saying it converges. And otherwise, if your r is not in here, look, it's diverging, all right? That's what the else means. If r is else, something else than this, then it diverges. All right. Questions? God, 8.1 just keeps going and going and going and going. Some more definitions. This is a definition. A sub n is said to be increasing if a sub n is less than a sub n plus 1 for all n greater than or equal to n naught. You know what? Let's just put all n for now. Oh, yeah, sorry. Upside down capital A means for all. For all. For all n. Does that make sense? Let's say, let's just look at an example. This is saying a sub 1 is less than a sub 2. So it's lower than a sub 2, and then a sub 2 is less than a sub 3, and a sub 3 is less than a sub 4. So it's increasing as you read it left to right like a book. Okay, that's what it means to be increasing. What does it mean to be decreasing? Opposite, right? So this would be something like a sub 1 is bigger than a sub 2, which is bigger than a sub 3, which is bigger than a sub 4, right? And so as you move to the right, they're getting smaller and smaller and smaller. So we have two things here, increasing and decreasing. In either case, a sub n is called monotonic. So if I say that you have a monotonic sequence, that means it's either increasing or decreasing. Monotonic is more general. It doesn't tell you which one it is. So we have a monotonic sequence. It's either increasing or decreasing. You all okay with that? More definitions. A sub n is said to be bounded above if capital E backwards means there exists a capital M such that, ST means such that okay? Such that A sub n is less than capital M for all n. A number. So think of it as M is like a ceiling. It's like the roof. And your sequence stays below that all the time. So it would be bounded above. You could say that if you took everyone's height, right? Everyone stand up and we measure your height. We would say that the height of the ceiling is creating an upper bound for us, right? We are bounded above by the ceiling. Make sense? And then if you have the idea of bounded above, then obviously you'd have the idea of bounded below, right? So that's the next thing. A sub n is said to be bounded below If there exists a little m such that, how do I write this one? A sub n is greater than little n for all n. So that's the floor, right? That's the floor. It's a lower bound. If a sub n is bounded above and below, it is said to be bounded. I've never liked this, okay? I've always had a problem with this. I think that they should choose a different terminology for this. Because what this is saying is that if I say that a sequence is bounded, it has to be both bounded above and below. If I say a sequence is bounded above, it's only above. Bounded below, it's only below. So if I tell you, hey, a sequence is bounded, you may think, oh, well, that means it could be above or below, right? It's actually above and below. So being a bounded sequence is a very strong condition. It means that there's not only a ceiling, but there's a floor that's going to control the sequence. If it was just the top, it would be bounded above and unbounded below. Sine and cosine are bounded sequences. Sine n, cosine n are bounded sequences. Yep. Okay, now from this, we get what's called the monotonic bounded sequence theorem, okay? Yeah, I know. Bounded. Let me do an example before we do that. Hold on. Show a sub n is bounded is a sub n monotonic. Here's a sub n. So what I like to do is I like to first just write out what a sub n is. Just start writing out terms, pieces of the sequence. So plug in 1, what do you get? 0. Plug in 2. 1 minus a half is 1/2. Plug in 3. 1 minus a third, 2/3. Plug in 4. 1 minus a fourth, 3/4. Then 4/5, and it keeps going, right? Okay. Is it bounded? Well, bounded means it has to be bounded below and above. Well, it looks like none of these problems, or none of these things will ever be negative, right? So do you agree that a lower bound would be like -1? Yes? Let me check. Is a sub n bigger than -1 for all n? Question. Is 1 minus 1 over n bigger than -1? That's what I'm asking, right? You have to show me that's true. I'm not convinced yet. Show me that's true. So just solve this inequality. So what I'll do first is I'll move this. How about I move the -1 over to the left by adding 1 to both sides, and then move the -1 over n to the right by adding it to both sides. And so I get this. 2 is greater than 1 over n. Are you convinced that that's true? Me too, but we can go one more step. How about we multiply both sides by n? Do I have to worry about flipping the inequality? No, because n's a positive number. So this is saying 2n is greater than 1. Are you comfortable with that being true all the time? Let's go one more step. Divide by 2. Is n greater than 1/2? Yes. Why? Because we're starting at n is 1, right? So I started with something that, yes, you can see in here it's never negative. But do you see how actually algebraically went through here and solved the linear inequality and got it to a point that everyone can agree with? That's what you have to do. And get used to this, because it's going to be coming up a lot, all right? Take it to the point where there's no arguing about what it is. It says, oh, yeah, that's obvious. No, this is obvious. No, this showed it's bounded below. All that did was showed it was bounded below, right? So this right here, since this is true, therefore, a sub n is bounded below. I don't have to say what it is, okay? This does not, what you're referring to, I think, is trying to find the lowest one. That's called the, sorry, it's been a while, greatest lower bound. You're trying to find of all, I mean, because there's a bunch of lower bounds. -2 is another lower bound. -5 is another lower bound. What's the greatest lower bound? That's a totally different question. That's not what we're looking for. Okay. Try something else. Yeah. How would it? I don't know. We'll have to see. Yeah. The pattern is in here. I mean, you're going to have to look and see through here. Do you see something? All of these were positive. So that made me think, let's just pick a negative number. -1 seemed good. Now let's, because we have to show it's bounded, right? I've shown half of it. I now need to show that bounded means bounded below and above, right? Now I need to find an upper bound. What is something that looks like is always bigger than these? 1, right? Doesn't that look right? So we have to show it. So I'm asking myself this question. Is a sub n always smaller than 1? That means is 1 minus 1 over n smaller than 1? 1. How about canceling 1 on both sides? Is that true? Are you convinced with this? N is a positive number, right? So -1 divided by a positive number is a negative number. Negative number is less than 0. I'm convinced with that. I could also multiply both sides by -1, or sorry, by n, right? If I multiply both sides by n here, what would I get? This is true. It's true always. As long as the n I multiply by was positive. Because if it was negative, it would have flipped the inequality and then it wouldn't have been true. But my n is always positive. Okay, so therefore what? Therefore a sub n is bounded above. Therefore a sub n is what? Bounded. Okay, I have shown that it is bounded because I have found a lower bound and I have found an upper bound, and I showed the inequalities, right? I had to show that was true. I had to show that was true. Once I showed those two things were true, I've showed it's bounded. I'm not done though, right? What's next? Is it monotonic? Monotonic means one of two things. It's either increasing or decreasing. So are these things getting bigger or smaller? They look like they're getting bigger, don't they? So I go back to the definition. What does it mean to be increasing? This right here, right? I have to show that's true. I have to show that a sub n is less than a sub n plus 1. That's what I have to show. Y'all ready for me to show that? Pay attention to how I do it. So monotonic. Question. My bet is that it's increasing, okay? That's right. You've shown just one. Yep. Yep. So increasing. So this is a question. I think it is, right? But I'm going to check it. So I want to show WTS. I want to show WTS. Want to show what does it mean to increase? A sub n is less than A sub n plus 1, right? That's what I want to show. What is A sub n? 1 minus 1 over n. Ugh. I want to show that that's less than 1 minus 1 over what? N plus 1. See, I'm replacing the n with n plus 1. I need to show that that inequality is true. It's not enough to just sit there and say, oh yeah, that's obvious. Look, they're getting bigger. I mean, I agree they are, but we have to be precise. So how about canceling ones on both sides? Subtract 1 on both sides? Yes? Then I have negative 1 over n less than negative 1 over n plus 1. And what I think I'll do now is I will change the sides. I'm going to add this whole fraction to the other side to make it positive, and I'm going to add this to the other side. That way I'm going to get this. By adding them to both sides, what I'm doing is I'm avoiding the flipping of the inequality. Because I always have to flip inequalities when I multiply, don't I? So this move right here could have been achieved also by multiplying both sides by negative 1. When you do that, though, what would you do? You would flip this, and then you would get 1 over n, positive 1 over n is bigger than this, which is the same as this. Y'all follow that? Okay. How about cross-multiplying? N less than n plus 1. Subtract n on both sides. You agree? That's true? 0 is less than 1. I have shown that it is, what, monotonic? Increasing. Now, just for the sake of demonstration, what if I thought it was decreasing? What would have happened here is this symbol would have been the other way around, right? Then this symbol would have been the other way around. Then this would have been the other way around. Then this would have been the other way around. And then this would have been the other way around. And our final conclusion would be that 0 is bigger than 1. And that meant it's not decreasing. Does that mean it's increasing? No. It just means it's not decreasing. You do not have to be increasing or decreasing. You can be neither. Sign. It's neither increasing nor decreasing. Any questions on this? Draw my conclusion. Therefore, A sub n is monotonic. Nope. Two separate ideas. I actually put more than just monotonic. I put monotonic increasing just to specify which one it was. It was increasing? Yeah. This inequality, the inequality would be the other way around. And it would have to be true.
Okay, so when you did the inequality the other way around, you were trying to, it did be true, but it didn't hold true at the end.
That's right. It wouldn't have. So it would have been incorrect for me to conclude decreasing.
So pretty much you just have to prove it.
That's right. All right. Yeah, can you all flip those back? I don't know why you did that. I'm just going to change the lighting scheme today. First two on the left off. There we go. That's the way we normally have it. All right, theorem. Every bounded monotonic sequence what? What's the last thing I put here? This theorem is saying that every bounded monotonic sequence must converge. Why? And we're not going to prove this theorem. Let's try and do it geometrically, though. Okay, so let's say I have a sequence, right? And it's bounded. What does bounded mean? It's got a ceiling, right? And it's got a floor. Okay? So that's what the bounded means. Monotonic means it's either increasing or decreasing. So let's just say it's increasing. So let's say it starts here and we're here, right? The next one must go above that. And the next one must go above that, and then above that. And as I keep moving to the right, it keeps on going higher. But I have a ceiling. It may not converge to the ceiling because the ceiling may be up here, right? And the points may keep on getting bigger and have some sort of asymptote here, right? But the fact that it's bounded is a big factor here, bounded below and above. Yes, it forces convergence. Yep. Monotonic takes that out. Can't do that. Exactly. So every bounded monotonic sequence must converge. So the sequence we just had a second ago, right? Right? The sequence we just had, this right here is bounded and monotonic, and it converges. Does it say what it converges to? It doesn't tell us any of that, right? Now in this one you can tell what it converges to because what's 1 over infinity? It goes to 0. 1 minus 0 should get close to 1. So this is converging to 1. The importance of this theorem is that sometimes you can't tell where a sequence is actually going, but you can show it's bounded and you can show it's monotonic. So you know it converges, but you know nothing about what it converges to. And sometimes just knowing it converges is enough. That's enough for us. All right? Questions? How about this? Jeez. How do I ever get out of this section in 2 days? Okay. How about this? A sub n equals this. Root 2, root 2 root 2, root 2 root 2 root 2, root 2 root 2 root 2 root 2, dot, 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 forever. What does A sub n converge to? Mm-hmm. Say again. Okay. Is the lowest. Okay. So it's bounded below. Up or above or below. Yes. Increasing one would be bounded below. Decreasing one would be bounded above. But you're not guaranteed the other part of it. Yeah. Okay. What does this converge to? So our best chance at this is to rewrite this I'm going to totally give this away, but I just want you to see how this is done. Okay, do you agree with this? This is 2 to the 1/2. This is 2 times 2 to the 1/2, all of that to the 1/2. The next one would be what? I'm going to keep going with this in a second, and the next one. What would this next one be? I know I have 1/2 out here. What is this piece in here? It's 2 times the previous one, which was 2 times 2 to the 1/2 to the 1/2. Do y'all agree with that? And then we could keep going with this, couldn't we? All right, let's try and find some sort of pattern here. This is 2 to the 1/2. And then what is this one right here? Let's try and figure out what this is. What's 2 times 2 to the 1/2? 2 to the what? 3/2, because you're adding exponents, right? It's 1 there. 1 times 1/2 is 3/2. What's 2 to the 3/2 to the 1/2? 2 to the 3/4. So this is 2 to the 3/2 to the 1/2. Now you multiply the exponents, you get 2 to the 3/4. Next one. What was this whole thing right here? 2 to the 1/2, 2 times 2 to the 1/2 to the 1/2. That was 2 to the 3/4, right? Times 2. 7/4 to the 1/2. 2 to the 7/8. God, maybe we need one more. Do you think we need one more? I'll just tell you what the next one would be. I'll leave it as an exercise. 2 to the 15/16. ... What's that? Converge to 2. What's happening to this right here? Look at the powers. 1/2, 3/4, 7/8. Okay, someone give me a formula here. A sub n is 2 to the what? Come on, you can do it. What is it? Okay, the denominator of the exponent is 2 to the n. What is the numerator? 1, 3, 7, 15. 2 to the n minus 1. 2n minus 1? It's always 1 less than what's on the bottom, right? So 2 to the n minus 1 up there? No. 2n minus 1 down here, right? Did y'all see that? Do you agree with this? So all of the numerators are just powers of 2, but take 1 away, right? This was 2, take 1 away. This was 4, take 1 away. 8, take 1 away. 16, take 1 away. Now, what is the limit now? What is the limit as n goes to infinity of 2 to the 2 to the n minus 1 over 2 to the n? Okay, so you have to look at this. That's infinity over infinity, right? So could you do L'Hopital on that? Yes, but you'd have to rewrite this function as a function of n, right? Let's just assume we went over here and we did, okay, this is a function of n, blah, blah, blah. We did L'Hopital. What's the derivative of top and bottom here? What's the derivative of the top? What's the derivative of 2 to the n? 2 to the n times natural log 2 over the derivative of the bottom, which is exactly the same thing. 2 to the n natural log 2. That's your derivative of top and bottom. That's 1, right? So this is going to 2 to the 1, which is 2. So this is converging to 2. 2 to the... That's weird, huh? Another way you could have done this without using L'Hopital, since you have 2 terms, well, I should do this one. 2 terms on the top, 1 on the bottom, split it into 2 fractions. 2 to the n over 2 to the n is 1 minus 1 over 2 to the n, which is 1 over 2 to the n. And now you don't even need L'Hopital because this goes to 0. 1 minus 0 is 1. That's just 2 to the 1. Could have done it that way. Trying to give you some interesting examples. Okay, one last one. Come on, 4 minutes. I can do this. A sub n equals n factorial over n to the n. Does converge or diverge? The top goes to infinity, bottom goes to infinity. Agreed? But you can throw L'Hopital out. That's never happening because we have a factorial, so that's automatically out, right? Let's just write down what n factorial is. It's n times n minus 1 times n minus 2, all the way until we get down to what? 1? Yeah, n minus n, which would be 0. But, well, we stop at 1. We don't stop at 0 because that'll kill everything off. What about the denominator? N to the n? Would you agree that these line up? Like, for every factor on top, there's an n on the bottom? Do y'all agree with that? Because n factorial, you should have n, right? If it was 4 factorial, 4, 3, 2, 1, and then this would be 4 to the 4, which would be 4, 4, 4, 4, right? You'd have 4 4s being multiplied. So this should match up, right? This is okay? Let's see if anything happens here. This cancels out, right? Yay! All right. Everything else, though, tell me about everything else. Take right now a limit. It then goes to infinity of this. What would this go to right here? Infinity over infinity. But you could use L'Hopital on that, couldn't you? You could? That's going to go to 1, isn't it? So that one should go to 1. What should this one go to? 1. What should this one go to? 1. All of them should go to 1 except the last one. It's going to go to what? 0. So the answer's 0. N factorial grows very rapidly. We know that. But n to the n is even faster. So it's going to infinity so quickly that it's squishing this ratio down to nothing. Make sense? You need to show it. Yep, you need to be able to show it. Okay, so for homework, we did not get out of 8.1, but we did finish 8.1. Make sure this matches up. (9 through 32), 37 through 40. Okay, next class we will start series. make sure you do your homework.